Good day, boys and girls. We are looking at software at grade 11 level. The topics that we're going to cover are types of operating systems, compilers and interpreters, overview of processing techniques, virtual machines, and virtualization. Software refers to digital items made up of ones and zeros. They tell your computer what to do. So software is instructions to your computer. It is also data for your computer. There are many different types of software, including system software. An example is your operating system. Then we have application software. Example is your Office. And in Office, we have Microsoft Word, Excel, and database, and so on. Games also fall under software, and utilities. Examples of utilities are your drivers, like your printer drivers. So your computer and your printer can communicate. System software is responsible for managing your computer and translating the instructions from your software to a language your hardware can understand. The most important type of system software is the operating system. For example, Windows 10 that we're using at school. Tasks of the operating system. One, it manages and interprets signals sent and received by hardware. Understanding and communicating with different hardware devices using drivers. The operating system also manages computers' memory and storage. Memory is your RAM, manages how your RAM is used, and storage, for example, your hard drive, reading and writing from your hard drive. Monitoring your hardware's performance, providing an interface for users to interact with the computer. That's your graphical user interface that you use in Windows. Allows the computer hardware to interact with its software, and allowing computers to connect and communicate over a network. Now we're looking at the different types of operating systems. The standalone. For standalone computers, that's your desktop computers, to manage the hardware and software of a computer and to provide a user interface for computer users. So your operating system will manage your standalone computers, the hardware and software, and it provides a user interface. And these standalone software operating systems are used for almost all home, office computers, and smartphones. Your network or server operating system, it is used to provide a service to or manage computers connected to the same network. Remember, it also forms a backbone for the largest network, the internet. Your embedded operating system is designed to run the software for a specific appliance or device. It's built or embedded in the device. Example, your smart TV has an embedded operating system, as well as your video camera. In terms of cost, there are many open source operating systems that are free. Open source operating systems are free. Most people on desktop computers use Microsoft Windows 10. And the cost of this is between 1,000 and 3,000 rands. For your network, we have the Linux-based network operating system. It is very popular and it is free. We also have Microsoft Windows servers, which costs in the range of 6,000 to 90,000 rand, depending on the server and the network for which it is used. In terms of your embedded operating systems, they are almost always sold as part of the hardware device. You cannot simply purchase a smart TV without an embedded operating system pre-installed. So embedded is built into the device. In terms of size, your standalone is small to large, the operating system. There are a few operating systems that require 1 gigabyte or less storage, but Windows 10 requires 16 gigabytes of free disk space. For network operating systems also serve from small to large, the size. Most network operating systems require a significant amount of free disk space. The size also depends on the network it is serving. The embedded operating system are very small. They're built into the device. The hardware for standalone is your hard disk drive. Your operating system will be stored on your hard disk drive. You've got your CPU that is working with an RAM, your memory, into which you load your operating system. Network operating systems require a network interface controller. Your embedded works with processor, RAM, and ROM. Examples of standalone is your Windows Home Edition and Ubuntu, which is free software. In the server, we're looking at Windows Server. There's also Red Hat Server. They are your operating systems. The next aspect we're going to cover are compilers and interpreters. Now, in most modern programming languages, the programming code is simple, easy to read, and easy to use. Programs, however, written in machine code is difficult to read. So you are using our modern language, Delphi, which is easy to read. It's close to the English language. Machine code refers to the instructions delivered directly to your CPU and is written in binary or hexadecimal, and it gives instructions on what to do. So machine code is delivered directly to your CPU. Now, this might include references, your instructions that is might include references to memory addresses, logical operations, or any other instruction for your CPU to complete. So your CPU can only work with your machine code. Programming code must be converted to machine code for the CPU to use. To do this, we use an interpreter or a compiler. Now, with Delphi, it's written in high-level language, we will say, which is close to English, and it needs to be converted to machine code. So the question is Delphi using an interpreter or compiler? We'll answer that soon enough. Your machine code definition, the executable instruction code provided by all running computer system programs and applications. So machine code is normally your EXE executable code. All right, so we spoke about interpreter and compiler. And if you look at the bottom here, interpreter examples are JavaScript, Python, and Ruby. And compilers are basic C++, Delphi, and Java. So Delphi is a compiler. Now the difference between an interpreter and a compiler, both converts to machine language, but in different ways. Now your interpreter interprets and sends code to the CPU line by line. The compiler translates and compiles an entire program before sending it to the CPU. So a compiler compiles an entire program, and the interpreter works line by line. It is faster to open a program if you're using an interpreter, but slower once opened. It's slower because each line is converted and run. Your compiler is slower to open a program because the entire program has to be compiled. And once it's compiled, then you can run. So it's faster once you have opened it. The interpreter continues interpreting and running code until an error occurs. So it's running each line, and if an error occurs, the program will crash. So it interprets each line until an error occurs, and at that point, the program crashes. Your compiler, it stops compiling the moment an error occurs. So there's no running of code. The entire program is compiled to machine code. And if an error occurs, then it will stop compiling, and which means the program doesn't open. So again, those are examples of interpreters and compilers. The next concept now is overview of processing techniques. The CPU completes tasks using the following techniques: your multitasking, multiprocessing, multithreading. Multitasking is the ability of the operating system to quickly switch between many computing tasks, so the different applications appear to be executing simultaneously. So if you're running more than one application, multitasking allows the operating system to switch between tasks that need to be executed. So it appears that they're being executed simultaneously. For example, if you're burning a CD while you're reading from your keyboard, then the tasks, if multitasking is taking place, then both will appear to be run simultaneously. But the operating system is allowing actually a switching between tasks. Multi-threading. Operations within a single application can be divided or are divided into threads. So what's a thread? A thread is a way for a program to split itself into two or more simultaneously running tasks. So ability of a program to split itself into two or more tasks. And examples of that is when you're downloading a file from the internet using your web browser, but you're continuing browsing. So you're doing two tasks. You're downloading and you're browsing. So these are thread. Each one is a thread. Downloading is a thread and browsing is a thread. That's through one application. That's using your web browser. Another example is when you're typing, when you performing and the computer is performing a spell check in Word. So that is, these are two threads being run in Word. So again, multi-threading is operations within a single application that are divided into threads. Each of the threads can run in parallel. So they run simultaneously. The operating system divides processing time among each thread within the application. Now, multiprocessing, similar to multitasking, but it has multiple processes. So it uses multiple processes to complete tasks simultaneously. So instead of switching between tasks, each task is handled and run simultaneously. Today, many CPUs are made up of more than one processor. They're called a core. Each core is then able to complete program instructions on its own. Multiprocessing is because CPUs have many cores. That's the reason. Now, looking at this example here, it says a CPU with 4 cores should be able to complete 4 times as many instructions as the same CPU with only 1 core. However, this is not always the case. For example, in most applications, the instructions needed to be executed run one after the other. So cores cannot complete the first and last instruction simultaneously. So although you may have multiple cores or 4 cores in this example, but if your instructions need to be executed in order, then the cores cannot execute the instructions simultaneously. You have to wait for the one to be executed before you proceed to the next. So it all depends on the execution of the tasks. Multi-core processes therefore allow you to process multiple threads or multiple processes more quickly, but may not improve the performance on any single process. So it all depends on what has to be executed. But if there are multiple threads in a program or an application, the multi-core processes allow you to execute the multiple threads. So that's where it saves time. Now look at this example, the AMD Ryzen 5 1600X CPU has 12 logical processes. So the figure alongside shows us how much each of these processes has been used over the last 60 seconds. This is from your task manager. There's the 12 processes and you can see how much is being used in the last 60 seconds. You can open your task manager on your computer by right-clicking on your taskbar at the bottom and open your task manager. And when you go to processes, performance, processes will give you your processes, but performance will give you your CPU. You can see the cores of your CPU and how much of work each core is doing. That's an example that you can look at. Your next concept, last concept, is virtual machines and virtualization. Virtualization is the act of creating a virtual device using software. Each virtual device acts as a node and is allocated its own virtual hardware, like CPU, RAM, and storage space. Now, if we look at this example here, the original computer, the host hardware is your original computer. It's called the host. That's your original computer. Host operating system, that's your original operating system. By using virtualization application here, you are now able to divide your computer into three. In this example, it's divided into three guest computers. So we have, or three virtual machines, we can call them. It's all built on your original machine. So these three virtual machines can install, each one of them, you can install an operating system, and the operating system is allocated its own virtual hardware. So from your CPU for your entire original machine, you allocate a CPU for each of your virtual machine. You are allocated RAM and you allocated storage. So it's one machine, but using virtualization application, you're able to now create three machines. They are virtual machines because they are not physically three machines. Examples of virtualization software is VMware, Workstations, SolarWinds, Virtualization Manager. And your reasons for using virtual machines. They allow users to install different operating systems. So if you want to test out an open source operating system like Ubuntu, then you can use your virtual machine without interfering with your original computer. Virtual machines can be used to install an application that might contain a virus. Testing it on a virtual machine will allow you to see if the application contains a virus. If it does, you can simply delete the entire virtual machine, so it does not affect your original computer. The image of the virtual hard drive can be used to back up your computer or to transfer all your data to a new computer. Also, virtual machines enable mobile developers to develop applications for different versions of Android and iOS without having to own hundreds of different devices. So if you need to test an application, it's easier to install the different versions of your Android operating system on your virtual machines and test there rather than buying these devices for testing purposes. Those are the advantages of virtual machines. Your application is from your DBA textbook. This is a section, all these sections have been covered from your DBA textbook. There's your application activity 2.1 to 2.5 and your consolidation activity on page 36.